in this design, in this truncation type of design, there's really nothing to design. The only thing that we can design is this L. This is truncation, this L. The only thing that we can design here is L, right? You just determine L and then you just take a chunk of the ideal low-pass filter and that's it. There's really nothing to design, right? So, and we know the window function always this is the rectangular window, right? The frequency response always look like this. And this slope is kind of fixed. This slope is kind of fixed, okay? So there's no control over this side lobe because the rectangular window function is a fixed function. So in the frequency domain, what we will get would be a fixed thing. If L is fixed, then everything is fixed already. Okay. So people start to think about different way of designing the window, and there are many windows that are designed. So let me write down some of those windows. So people start to look at the more general window design. Oh well, maybe I skip one thing. The window itself, there's the only parameter is L, right? And then there's the ideal low-pass filter. What kind of ideal low-pass filter? There's still that cutoff frequency that we can shift around. Okay. So more general window, HN is designed like this. So first of all, we can shift the ideal low-pass filter around, so that it's already causal to start with. Okay. And then this WN is is 0 for n larger than n and for n smaller than 0. Okay. Okay, then we will automatically get a causal filter at FIR filter of order L, of order n. Okay. And so the first thing, one thing we can design is this omega c, and then we can also design this WN. Okay. Just now when we do this truncation, what we are really doing is we are multiplying the ideal low-pass filter with a rectangular window. So instead of rectangular window, we can multiply it with a different window. That's a possibility, right? So one thing is a rectangular window, that's what we already know. W is the rectangular window. In addition to rectangular window, there's a Hemming window. But actually there's also a Hemming window, two different people. WN look like this. Hemming window, okay? And then there's something called Blackman window. From what we can see with the Hemming window, it's a cosine function. It's a cosine function. And then 0.54, and there's a cosine function that gets subtracted, okay? And the Hemming window has a constant term and a 2 cosine, right? And let's see in the picture, let's look at the view graph to see how they are different in time domain, okay? So people start having different window, right? And let's see how they look in the time domain. Okay. All right. So this is how they look in the time domain. This is a rectangular window. N is equal to 20, so there are 21 coefficients here. And if we use the rectangular window, then it's from 0 to 20. It's just 1, right? Okay, the blue line. Here I don't draw it using stem. I just connect the whole thing, okay? And then there's the Hemming window. Hemming window is the green one. It's the green plot, okay? And the Blackman, that's the Blackman. And from rectangular to Hemming to Blackman, we can see the shape is a little bit different, okay? The rectangular window is just 0 and goes up and then coming down again, right? And with the Hemming window, it's sort of taper on the two sides. It's coming down on the two sides. Okay, that's Hemming window. And with the Blackman, it's coming down further. on the two sides, right? It's coming down, like so. That's the shape, okay? There, the window becomes more tapering off at the two ends. So that's the time domain, right? But remember, the window has an effect on the final magnitude response in terms of main lobe and side lobe, right? So let's look at the main lobe and side lobe of these three different windows and see how they behave in frequency domain. So here we go. This is what it looked like. The blue line is a rectangular window, and that's the Hemming window. Hemming window is the green one, and Blackman window is the red one. So which one has the, what can you say about the shape? What can you say about the main lobe? That's the window itself, the magnitude response of the window. Okay, what can you say about the magnitude response? The main lobe. Which one is the widest? Which one has the widest main lobe? The red one. The red one is the widest, right? Okay. So in terms of main lobe width, we have Blackman, rectangular is the narrowest, followed by Hemming and then Blackman. Okay. So that's the magnitude response. Now let's look at dB. Okay, that's the dB plot of this figure. Exactly the same thing, only we're drawing in dB. Okay, then what can we say about the side lobe? Who has the smallest side lobe? The red one has the smallest side lobe, right? Okay, so when we look at the main lobe and the side lobe, we see that in terms of main lobe, the rectangular has the smallest main lobe, okay? And the Blackman has the largest main lobe width. And in terms of side lobe, the red one has the smallest. So Blackman has the smallest side lobe, and the rectangular window has the largest side lobe. Okay, and remember, these main lobe and side lobe are going to affect our final filter, right? This is just the window. This is not our final filter yet. We're gonna, in the time domain, we multiply the window with the ideal filter together to get our final filter, right? And the main lobe and the side lobe of the window are gonna affect the pass band, stop band, and transition band of our final filter. And here we go. Maybe let me ask you this question. Who do you think would have the widest, or the narrowest transition? Which window will give you the narrowest transition? Rectangular window will give us the narrowest transition, right? Okay, very well. And which window will give us the best stop band? The Blackman will give us the best stop band. All right, so now let's look at it and see if our conjecture is correct. All right, and this is the magnitude, and that's the dB in dB plot. And we see the blue one indeed has the sharpest transition, right? But if we are looking at the stop band, then the Blackman window has the best stop band. It has the smallest stop band ripple. So now we are faced, the problem that we have is here. If we have different window shape in the time domain, then we will get a different main lobe and side lobe. And it's really a trade-off, right? When we have the best transition, then the stop band is not so good. And if we have the best stop band, then we have the widest transition. So different window really gives us a trade-off between main lobe and side lobe. And this trade-off will in turn give us the trade-off between transition and stop band attenuation. In the window itself, it's a trade-off between main lobe and side lobe. And in the final filter, it's a trade-off between the transition band and the stop band. Okay. If we have different window shape, then we will get different trade-off. But in photo design, what we are really looking for will be a quick solution, you know. I tell you the spec. then how can you design the window? How do we know which window fit our, is the thing that we are after? Okay, so it would be great if I tell you the design and then you can tell me the window shape that I need to use, and the order of the filter that I need to use, and then the final filter, because that's the final filter that we are after. Right. Now that we know the trade-off, but we still don't know how to find the window shape that we would like to have. And that's when Kaiser comes in. So for a given set of specification, we would like to find the required order, and we would like to know the window that would meet the specification. And Kaiser comes in here. Kaiser, he said that I will give you a formula of the window. Just tell me your specification and I will tell you what the window to use. Okay? And this is the window that's used by Kaiser. It's a Wn is given in this form, and this I0 is a modified Basel function of the first kind, and it's given like so. That's I0x. Okay, I0x is like that. So the coefficient of the window function, we just plug in that Basel function, and then we will get the coefficient of the window function. Okay. And what is there to design? What is there to design here? We have a, remember, for different trade-off, we need a different shape, right? We need different shape of the window to get different trade-off. And in here, Kaiser window is different from all that hemming window and Blackman window and rectangular window in the sense that it has a parameter that controls the shape, okay? It has an additional parameter beta. You see there's a beta in there in the function, and this beta controls the shape of the window. In addition to the window length, it has an additional parameter that controls the shape, okay? And so let's find it out. Let's see how the variation of beta will give us different window, right? So here is Kaiser window. On the top here, what we have is a rectangular window and hemming window and Blackman window. Okay, that's something that we have already seen. And on the bottom here is window generated using this Kaiser window function by choosing different value of beta. So for example, if we choose beta to be 0, then it's the blue line, and that's the rectangular window. And if we choose beta equal to 5, then this is the shape. This is the blue. This is the green shape. And when we choose beta equal to 9, this is the red one. Okay. So well, actually, they are quite a family. There are quite some different window functions in addition to the one that I have just mentioned. There are many, many different window functions, and it seems all these different window functions can be approximated well by Kaiser window. Okay. We just change the value of beta, then we can approximate all those windows that we have just mentioned. Okay, because this beta will be able to control the shape of the window, and we will get different trade-off between the main lobe and the side lobe. Okay, so the commonly mentioned window, bar lip, hemming, Blackman, they can be approximated using Kaiser window. Here we have a Kaiser window for different L, okay, for different, meaning different window lengths, okay? And this is Kaiser window when this is the blue one. The blue one corresponding to n equal to 8, and then the green one is 20, and the red one is 80. Okay, so this is the window. Okay, and this is the we multiply it with the ideal low-pass filter, then we get the final filter, right? This is the blue, the red, and the red. This is the filter, and that's the window function, okay? The Kaiser window has two parameters, right? First of all, there's the beta, they control the shape, and then there's the length of the window, okay? So it has these two parameters. And we already know that for a given window length, beta control the shape, and it gives you the trade-off between this main lobe width and the side lobe width, right? So now let's look at what we can play with the different lengths. When we show the frequency response from different L, that's what we get, okay? That's H using 3 different window sizes. And that's the entry response, that's the in dB plot. And we have this corresponds to the short one, and the longer one, and the longest one. The short window, the medium window, and the medium length window, and the longest window. This is the final magnitude response of the filter, okay? And what we can see is that if we just draw a line here, okay? The stop band attenuation are, well, this side lobe looks like wider, right? I'm sorry, this ripple looks wider. But if we just look at the height, right here, right here, right here, right here, right here. Well, the length of the window is very different. But when we look at the stop band attenuation of the final filter, they are not so different. The stop band ripple here are kind of similar. So one thing that we can conclude here is that if we are given given beta, the window shape, okay, the 3 windows that we seen earlier, they are all for the same beta, okay, they are of the same window shape. And this stop band attenuation of the final filter is not affected by changing the window length. So the window length, what the window length affects is the transition band or the main lobe width, but not really the stop band. Okay. So this gives us an idea how to design the window. And this figure is similar for a fixed window length, and we change beta, then the result will be similar to what we have seen in the rectangular versus Hemming versus Blackman window. Okay, the window length is fixed, only the window shape is different beta, then we just get different trade-off between this is ripple size and the transition. Okay, ripple size. So from this picture, what we know is we can just, this length affect this transition, but does not affect this delta 2, right? And delta 2, this ripple size is affected by the window shape. It's affected by the window shape. Okay. So window shape is determined by beta. So from the ripple size, we can determine the window shape. We can determine the window shape. And then we can determine the transition using the window length. So these 2 things sort of decoupled. Okay, first we want to design the main lobe, the transition and the stop band, right? But now we see that we can use the window shape to determine the stop band. Okay, the window shape will determine the stop band, and then to get a sharper transition, we can use the window length to give us a sharper transition. All right, so that's the procedure for Kaiser window design. We have this, first we still have the ideal low-pass filter cutoff frequency to determine, right? So this cutoff frequency, we can take it as the midpoint between this passband edge and stop band edge. And then we determine beta, the window shape, using the stop band ripple size, delta 2. Delta 2 will be taken as the minimum of delta 1 and delta 2. For a given specification, we have delta 1 and delta 2, right? But in window design, we have delta 1 similar to delta 2, so we take the minimum of the 2. And then we get delta 2, that would be the minimum. And then we can compute the stop band attenuation, AS. And we simply use AS to determine beta. And this is a sort of this result must be sort of curve fitting. They do an extensive set of experiments to come up with this formula. They try to observe the relation between AS and beta and do curve fitting to come up with this formula to tell you that when the stop band attenuation is so much, then we use so much data. We use the beta computed like this. Okay, so for example, if you have stop-band attenuation in this range, AS is between 21 and 50, then we will plug in this formula beta, determine beta using this middle one here, then we can determine beta and the window shape. And then using the transition, we will be able to estimate the order of the filter. Okay, this N, there's AS at the top, and then there's a transition band at the bottom. All right, and there's the final window. So that's Kaiser window design. Nowadays, it's quite easy to do filter design when you have MATLAB. Suppose, let's look at one example, okay? We have one specification of a desired discrete time filter. 1 minus delta 1 is minus 0.3 dB. Okay, usually we say delta 1 is like, delta 1, the actual value is delta 1 is a 0.114, but sometimes we specify in a different way. We specify 1 minus delta 1. Okay, 1 minus delta 1 is 0.8 something, right? And you take dB of that, it's a minus 0.3 dB. Minus 0.3 dB. Okay, there's just different way of telling you what delta 1 is. And then delta 2 is minus 50 dB. Okay, or 0.003422. Okay, and the passband edge is 0.2 pi, stopband edge is 0.3 pi. So we can use this to determine the cutoff frequency. That would be the middle, so 0.25 pi. And then we use the stopband edge, the ripple size to determine beta. Delta 2 is the minimum of 2, so we get delta 2 equal to minus 50 dB. And then we can use the formula to determine the value of beta. And after we have beta, we can use it to compute the window. And then using the transition band, we can estimate the order that's needed to have such a filter that satisfies the specification. Okay? And the order estimation gives us a 59. And that would be the final filter. Here is the final filter. Here we have delta 1, 0.0035. 0.0035. Remember, delta 2 is 0.0032. 0.0032, right? So the final delta 1 that we have here is 0.0035 because remember delta 1 is similar to delta 2, so the value is similar, so it's close to delta 2. And then we have this final filter. Here. The stopband attenuation, the desired attenuation is 50 dB, right? So this is around 50 dB, all right. This is a 0.3 pi, and this is 0.2 pi, that's the passband edge, okay? And one thing that's interesting to look at here is that the estimation of order. And the order is we haven't really talked about implementation yet, right? But what do you expect? The order, if we have a filter of a larger order, what would be the complexity of implementing the filter? Higher or lower? The complexity or cost of implementing the filter. Do you think it will be higher cost? It will be a larger cost, a higher cost to implement the filter, or lower cost? If you have a longer filter to implement. N is the order, right? A larger N means a longer filter. Okay. Would the complexity be higher or lower if you have a longer filter? 如果我们的那个 filter 的长度比较长的时候，那我们去把它做出来的时候，那个成本应该是比较低还是比较高的？应该是比较高的嘛，哦，那成本会比较高。所以通常我们在做这个的设计的时候呢，我们当然也希望我们这个 order 要越小越好，越小越好。OK， 那我们看到这个它的 order 会跟什么有关系呢？会跟我的 stop band attenuation 有关系。stop band attenuation 在分子的这个地方嘛，所以比方说我要的是50 dB 的话，那这里就50了50减掉7.95。然后还有一个呢，也很重要的是这个 transition band。transition band 是在下面的这个地方，所以呢 transition band 这个是非常直接的你看如果我的 transition band 变成是1半的宽度的话，那我的 order 会怎样？我 transition band 如果变成1半的宽度的话，我的 order 马上就变成了2倍了所以 transition band 的话呢，在这个 photo design 的地方，它也占得非常非常重要的角色，因为它就是直接就影响到了你所需要的 order。那所以如果我的 stop band attenuation 比较小的，我 stop band attenuation 的那个需求比较小的时候呢，这时候我的 order 也会比较大。如果我的 ripple size 要求的比较多的时候，就会比较大。所以应该是这样讲啦，就是你越像 ideal filter 的时候，这时候你所需要的 order 就会越大。那越像 ideal filter 是什么呢 ？stop band、pass band 的 ripple size 越小，因为在ideal 的 low pass filter 的时候，它的 pass band 跟 stop band ripple size 都是等于0的嘛，对不对？所以你在那里那个 ripple size 越小的时候，这时候你的要求就越严格，那这时候就所需要的 order 就会越高。还有呢，就是 transition。你的 transition 越窄的时候，越像 ideal low pass filter 的时候，你的所需要的 order 就会越高。那在这里呢，我们有一个在 window design 的时候，有时候我们会说这个是有一些部分呢是 overdesign 了overdesign 什么叫做 overdesign 呢？就是说我其实呢，像刚才的这个例子里面好了，我们的那个 delta one 呢，其实是可以到0.1多的。我们的 delta one 呢，它实际上是可以到0.114的 ，OK， 那是 delta two 很小 ，delta two 通常的那个 stop band attenuation 要求在有一些application 里面要求会比较高，所以它可能是50 dB 啊、80 dB 啊、100 dB 啊，好，那可是呢，在 window design 因为 delta two 跟 delta one 会很相近的关系呢，就会变成 delta one 也会变成很小。delta one 也会变成很小，那你可能会说呢，这个很小有什么关系很小很好啊，反正就是符合那个，因为它要求是说你要在1跟1减掉这么多里面，在 pass band 的时候是1跟1减掉这么多里面，这里面动嘛，对不对？要求是这样子嘛。那你现在如果 pass band 的 ripple size 更小的话，那不是就是还是符合那个 spec 啊？对不对？所以这个没有问题嘛，还是符合那个 spec。那这样子有什么问题呢？那因为我们刚才在讲说我所需要的 order 呢，跟我的那个要求有关系我们的 spec 如果要求的越严格的话，那这时候我所需要的 order 就会越高。那我们如果看这个Kaiser Window 的话呢，我们会发觉呢，常常也许我的 stop band 是要求比较高，然后我的 pass band 要求不需要这么高。可是因为 window design 它本身的关系呢，就会使得我的 pass band 呢，它的 ripple size 也会很小。那变成小的话呢，可是我们知道说，如果它越像那个 ideal low pass filter 的话，我的 order 就会需要越高嘛。所以一个可以想的就是说，如果我有其他的方式来 design， 然后我可以让我的 ripple size 呢，可以让它变得比较大，就是在 pass band 这里的话，它不需要求那么严格的话，那它会不会就可以需要比较少的 order？ 它不需要那么高的 order 就可以符合那个需求，就可以符合那个 spec 了。那这个是 window design 里面呢，我们会讲的这个下面有写的这个 overdesign 那其实另外一个可以看到它的 overdesign 的地方呢，就是我们看到那个 ripple size 那个 ripple size 是大小一致的嘛，是不是大小差很多，对不对这个 pass band 这边是 pass band 的那个 detail， 我们可以看到说它的 pass band 的那个 ripple size 其实是差很多的有些地方 ripple size 很大，有些地方 ripple size 很小，所以那最大的这个地方是多，如果符合了要求的话，那其他的地方当然也符合要求。可是对其他的地方来讲的话，这也是一种形式的 overdesign， 就是它会在这个地方，它其实它的可以容忍的那个范围可以是更大的，可是我们却没有 完全的利用到 spec 给我们的那个范围。那在 stop band 也是哦，就是这个地方的 ripple size 会是最大的。那接下来 ripple size 越来越大，可是我们看 stop band attenuation 都是看最大的那一个，所以就会变成说，这里是刚好符合需求，可是这边它却是 overdesign 的。那比较好的状况呢？什么是比较完全的利用到 spec 给我们的那个自由呢？就是说，是不是我们如果可以，它都是 equal ripple 的 ？equal ripple 的话，就是说这些 ripple size 都是一样的，在 pass band 也是 equal ripple， 然后而且是跟那个 spec 给我们的那个 ripple size 是一样的。然后在 stop band 呢也是 equal ripple， 然后那个所有的 ripple size 都是跟那个 spec 给我们的那个限制是一样的，那这时候我们就可以完全的利用到了那个范围，那这时候也许我们就可以得到一个比较小的 order。所以呢，在 window design 里面的话，我们就是因为这个 delta 1等于 delta 2的这个限制哦，所以就会 over design either in pass band or star band。那and it's non-equal ripple. So there will be over-design part of the pass band and stop band. And an optimum FIR filter, we would, for a given spec of the filter that satisfies the spec with the smallest order, we would like the filter to have the smallest order, there will be equal ripple in the pass band and the stop band with the specified ripple size. Okay. Parks-McClellan is such an algorithm that will give us an FIR approximation, an optimum FIR approximation. Given the passband ripple size and the passband edge and stopband edge, we would like to find the equal ripple FIR filter with the smallest order that meets the specification. And the Parks-McClellan algorithm is such an algorithm that will give us such a filter. I think maybe we can just look at one example. This is the same specification that we have earlier. Like in the Kaiser Window example, we have a passband edge 0.2 pi and stopband edge 0.3 pi, passband ripple size minus 0.3 dB, and stopband attenuation 50 dB. Okay, and here's the magnitude response using the Parks-McClellan algorithm. It also has an order estimation formula. Okay, and we can use it to estimate the order. And the order that's needed in this case, n is equal to 45. What is the order that's needed for such a specification in the Kaiser Window example? It's 50, what was it? 59? Was it 59, right? So in this case, we only need 45. And we look at the pass band, okay? This is a minus 0.3 dB, and it's equal ripple in the pass band, and also equal ripple in the stop band, and all the ripple size are 50 dB. Okay, and here's a comparison of the two. Which one do you think is the Kaiser Window? Which one is the Kaiser Window design? Which one is the Parks-McClellan? We have two things here. Which one do you think is which? The blue line is Kaiser or McClellan? The blue one? The Kaiser window design, right? Because it's a very small passband ripple size compared to the Parks-McClellan method. Because the specification said you can have the ripple size minus 0.3 dB, right? But in Kaiser window, the ripple size becomes very small because of the stop band, of the small stop band. Okay, and in the stop band, we can see the difference as well. Which one is the Kaiser window design? The blue one or the green one? The blue one. It's not equal ripple, right? The ripple size gets smaller and smaller. But as in the green one, it's all equal ripple. Okay. So because of the fully exploitation of the freedom in the specification, we can get a smaller order. Right now, it's very easy to design these filters using MATLAB. Okay. So, we have a Kaiser ORD, FIR1 that would, using these two. Kaiser ORD is the command for estimating the order that we will need with the Kaiser window design. And then FIR1, it will use the window to design the filter. Okay, that's FIR1. And then we also have a Rames OR. Rames OR is a Rames exchange. That's the order estimation for McClellan algorithm, Parks-McClellan algorithm. Well, Parks and McClellan. These are the name of two people. Okay, McClellan is a student of Parks in Georgia Tech. Okay, and then he came up with the algorithm when he was doing his thesis. McClellan was doing his thesis under the guidance of Parks, and he developed this algorithm, and this algorithm was named after these two, Parks-McClellan algorithm. Okay, and in the algorithm they use something called Rames exchange, so that's why it's called Rames order estimation, Rames order, and there's the. So using FIR1 window, and using this Kaiser order, we will be able to estimate the window length and the cutoff frequency. And we will be able to estimate the order. And with the window and the cutoff frequency, we can get the FIR1. Okay. And in this, the default window in MATLAB is a Hamming window. So if you want to have a Kaiser window, then you can use the Kaiser org and Kaiser window to come up with a window and then use it in FIR1. Okay. So there's the Kaiser org that you can get using the parameter, you can get the order. Okay. And we can also, it doesn't have to be an ideal low-pass filter. We can use other ideal filter to begin with. For example, a band-pass filter or a high-pass filter. For whatever ideal filter, we can always derive the ideal filter. It can be a band-pass filter, ideal band-pass filter, or it can be an ideal high-pass filter, or it can be an ideal band-stop filter. Band-stop filter. Well, this is 0 and this is pi. 0 and then pi. 0 and then pi. Like so. Okay. And in the MATLAB that we are going to do, have you had the chance to look at the MATLAB file? Well, we have this jammed signal, right? And you probably need to look at the property in the time domain and frequency domain to determine what kind of filter that you need. Is it a low-pass filter that you need, or a band-pass filter you need, a high-pass, or a band-stop filter? Okay, depending on the noise that's used to jam the signal. All right.